Well, sunshine, I want to talk to you today about the piston. Some of the things we've done to it, some of the benefit, how we changed timing inside the cylinder, partly with this piston, how we redirected, also some physics on what the rod thinks this piston weighs. Stock, the rod thought this piston weighed over 1/4 of a ton, over 250 kilograms, and how much we lowered it, so how much the rod thinks we lowered it, and how many free RPMs we get out of that, meaning how many more RPMs we can turn before we're up to the stresses for which that rod was designed. We can gain RPMs without putting, as far as the saw knows, without putting added stress on it. Stick around with me, let me know what you think. I ain't gonna interrupt this video anymore by asking you, but if you liked it, like it. If I didn't earn it, don't. Might consider subscribing if you would too. Pretty new channel here, trying to grow. If you think other people might enjoy this, do that thing. Without further ado, here we went. Today we're going to start doing the porting on this saw. I'm probably not going to show very many steps along the way, but I will show a few key moments. Where I'm going to start with this one is getting the baseline measurement. We've got an aftermarket 026 cylinder. The stock cylinder ran okay, but this is a big bore, and it run dismal compared to the stock cylinder, even though it was smaller, but we know why. With the base gasket on it, stock cylinder exhaust was 99 degrees. On the aftermarket, the base gasket made it thick enough. We was at 93 degrees exhaust. It had like no compression. The squish was 43 thousandths. On the stock one, the squish was, I'll see it wrote down, I know what it was 30 thousandths. But anyhow, and that raised the intake up to 66 degrees, which is 122 degrees of timing. And the intake on the stock one was 140. So anyhow, we're going to do some piston work. I'm not going to bore you with all the piston work in there, but we'll see what we got. Let's first, I want to get us a weight on this stock piston, rings, wrist pin, and bearings. Everything except for one little bitty circlip. I guess I can throw it on there as long as I remember to throw it on there later. We're at 73.00 grams right now. 73.00 grams. So that's going to be important for us. And the reason that's important, chainsaw make, let's say 13,000 RPMs. That means piston changes direction 26,000 times a minute. That's pretty violent. And if you can get this lighter, less stress on the rest of the moving components. So you don't want to sacrifice strength, but lightening it up, and we'll get rid of some of the casting imperfections that this is just natural with the factory. They're not going to take and smooth out every corner. They're going to make this thing, throw it in the box, and make the other one about 400 or 500 times a minute probably. We'll do some piston work on this and bring it back here in a bit. I'm not really trying to lose weight so much off this piston. It's curious to know how much you know or lose, but all these little casting marks can go. They also impede airflow. These little machining marks right here can go. All these sharp edges need to go. Any place there's a sharp edge has a place for it to crack. They need to be rounded and smoothed, in my opinion. The edges here can be smoothed off. We're not really looking for a weight savings. We'll have a weight savings. It's curious to know how much a weight savings it is, but I'm not doing this for weight savings. Now what I want to show you is some attention to detail. You can see in this little window right here, there is a lip, and that air has to come up through here, go out through here, and into those transfers. And you can see there's a little lip right here. It's just casting, but from the other side, it's just a solid drop off outside the piston here. I think just bumped the camera. Sorry about that. So you can see what I've done on this side. I haven't really removed any strength. All I did is radiused that lip right there, and I've got a little bit more to do, but I just want to take a moment and show that to you. It's the little bitty things like that that they can't do in the factory for productivity that you can do to your own saw. It's not structural, it's not needed, it's imperfections actually, and if you can take those out and smooth that up and let that air flow out there better, twofold, it'll make your piston better, plus you'll get more air fuel, and that means more power. Well, you can see we've opened these windows up just a little bit without sacrificing any strength. We didn't remove any of the strength material. We just blended corners like this one in here. Hopefully you can see that. All 4 of those corners we blended in. There could use a little more, can't it? But that'll promote airflow up out of the bottom of this chamber. It has to go out through these side ports. So anything we can do to let air go through there less restricted, the better off we're going to be. Let's see what kind of weight we got on it. You'll be surprised how much weight we didn't take off, but we helped airflow a bunch. Now, we can look at these patterns on top of this piston. FBI'd call those clues right there. This is where your transfer's feeding in. This is the intake side. Feeding fuel air mixture in. They're supposed to meet in the middle and then bounce towards the exhaust. You can tell, number one, they're not even from one side to the other. Needs a little bit of that work. And you can tell they don't meet in the middle. I want them to meet in the middle, and the middle of that piston is actually about right in there. So it's meeting off to this side over here, which means this transfer is feeding harder, and you can see that it is. And that's a nice thing about running them a little bit or working on a saw that's used. You can see, like I say, FBI call it a clue. You can see all kinds of little clues in there of what needs done or what it might like better, where the deficiencies are. Okay, we've about got the piston done. I'll bring it up here and show it to you. The weight of everything, the piston pin, bearing, rings, everything I've chose to go together as a unit. It's 69.47 grams, so we've saved some weight there. And I'll run that through the calculator and see how many pounds of force we saved. It's kind of staggering how much force this piston puts on. Let me bring this up and show it to you, show you essentially the finished piston. Now, of course, we smoothed out everything. We know that. We've already talked about that. Broke all the edges. There is a couple things I've done to this piston. I didn't necessarily like how the transfers were set, and the top of this piston actually blocked the lower part of the upper transfers. Plus, I didn't mind having a little less transfer timing due to where the exhaust was at. So instead of raising the transfers in the piston, in the cylinder, and I did do them a little bit, but I wanted to take some off the cylinder, I took it off the edge of the cylinder right here where the transfers line up on both sides, and I put this side just a little bit deeper, the intake side, so it will come out first. It will break first. And then on the intake timing, I got the intake where I wanted it, about the volume I think I wanted it, but I still wanted more intake timing. So instead of making that bigger, I took that intake timing off the skirt. You can see it here. I run it up to the timing I wanted, mark it, took it down to the line, and we'll time it. I'm going to run everything through the crock pot here and clean everything up. While it's cooking, I keep talking about piston weights, and we know lighter's better to a certain extent. The reason I was measuring it is because it's measurable, and I like numbers and calculations and one thing and another. So I went in the house and done the calculations while this was going through the first little stage. That original piston weighed 73 grams. And at 14,000 RPMs, the inertia force of the 73 grams would be 564.38 pounds. So essentially, in my understanding, that piston on the end of that rod, while it only weighs 73 grams, with this speed and change in direction, it's actually given the pull or the push of 564.38 pounds. Okay. Now, when I got that down to 69.5 grams, 69.47, I used 69.5. that lowered our inertia force down to 537.32 grams. So it lowered the inertia point by 27 pounds. I lowered the inertia force of this piston. Okay, so if I was running the original piston at 13,000, I can run my lightened piston to 13,324 RPMs before I get back up to the same inertia weight. You see what I'm saying? So I'm able to raise the RPMs on that saw. Raising the RPMs absolutely gives more inertia weight on your piston, rod stretch, everything else. You can mitigate part of that by the weight. I just gained basically free 324 RPMs that I can go up before I even start adding inertia that the rod for which it was not designed. So there's just a quick explanation of why I'm kind of curious about weights. Yeah, hope that helps somebody.